The last thing we need to talk about in Chapter 8 is factoring some special cases. So by the end of this lesson, that's what you need to be able to do, is factor and solve these weird things. So think back to when we multiplied. We had things that looked like this, where you had a plus b all squared. And remember, that meant you had to split it up into a plus b times a plus b, and then double distribute. But there was a pattern here. It was always the first term squared plus 2 times the first two terms multiplied together plus the last term squared. So if we do one like this, we can rewrite it like t plus 6 times t plus 6 and double distribute, or we could use the rule that says take this and square it, take this and square it, and then multiply these guys together, so t times 6, and double it. So this turns into t squared plus 12t plus 36. And if we double distribute, we would have ended up with exactly the same thing. There's our t squared. I have 6t plus 6t, which gives us the 12t, and then 6 times 6 gives us 36. So this pattern is what we're going to use to go backwards and to factor. If we notice something that fits in this pattern right here, we can just rewrite it like this and not have to worry about actually going through factoring by grouping or any of the factoring things that we did before. The other special rule that we learned was the difference of squares. So if you had two things that looked almost exactly the same, except one had a positive and one had a negative in between, our middle terms canceled out. So if we had something like this, d times d gave us d squared, this gave us negative 11d, this gave us positive 11d, and this gave us negative 121. We ended up with d squared minus 121 because these guys canceled each other out. Now the reason this is called a difference of squares is because we have subtraction. There's our difference. And this guy is d squared, and this guy is 11 squared. And those two things, d and 11, are what go here, separated by a plus sign, and then separated by a negative sign. So we're going to use these two rules, and we're going to go backwards and factor. You're going to start with something like this and give me something like that. Which brings us to this one. We'll do this one first because it's a little easier. The difference of two squares. So whenever you have a factor and you have two terms, from now on, I want you to check, is it a difference of two squares? So it needs to be subtraction, first of all. And then you also need to have two things that are squared, a squared and b squared. So like if I look at this one here, our first step, no matter what, is always look for a greatest common factor. And these guys don't have one. So then because it's two terms, I'm going to say, is there anything that I can square to get 81? And there is, 9. 9 squared gives me 81. And then is there anything to give me c squared? And there is, c. And then because this is subtraction, without doing a bunch of work around this, I know that this will factor into 9 plus c times 9 minus c because of this pattern up here. Anytime you have a difference of two things squared, it breaks up into this. Same thing with this next one. Always check for a GCF, and then once you find there is not one, check to make sure that you have a difference, so we have subtraction, and see if these two things are anything squared. So if I wanted to get 64g squared, I could square 8 in g, and if I wanted to get h squared, I could square h. So this 8g and this h are what my two factors are, 8g plus h and 8g minus h. Remember, just like anything that we've ever factored, you can check this by double distributing and make sure that you end up with what you started with. So let's try some more. Remember, the first thing you always need to do is check for a GCF. So if I look at 3a, I have a GCF. So I can factor out a 2, and I'm left with y to the 4th minus 25. Now what's left inside of here is two terms that are separated by subtraction. So I need to check, is there something I can square to get y squared? And there is. Or y to the fourth, sorry. Y squared gives you y to the fourth. And then this guy can be 5. 5 squared gives you 25. So this stuff in here factors into y squared plus 5 times y squared minus 5. And then I have to remember this 2 out front here. And both of these guys in here have 2 terms. This guy is plus, so I know he's not a difference of 2 squares, but this guy is negative, so he could be a difference of 2 squares. There is something I can square to get y squared, but there's not something I can square to get 5. So that's how I know that I'm done, and this is factored as much as it possibly can be. Let's take a look at 2a. So, look for a GCF. In this case, we don't have one. But there's 2 terms, and there's a subtraction here. So then I'm going to look for, is there something I can square to get y to the fourth? And we just answered that in the last one. There is. And there is something I can square to get 1. Just 1. So this factors into y squared plus 1 times y squared minus 1. Now before I can box this up, I need to make sure that I can't factor either of these 2 things. This guy has a plus, so he won't be a difference of 2 squares, but this guy has a minus. This one, I can factor again. If I square y, I get y squared, and if I square 1, I get 1. So just this guy right here factors into y plus 1 times y minus 1. And then we got to rewrite this guy here because we couldn't do anything else with him. So this is the factored form. I want you guys to do 2c, but I'm going to do 3c. So remember, first thing you always need to look for is greatest common factor. And in this case, we don't have one. So then it has 4 terms. And remember, with 4 terms, we got to factor by grouping. So we have an m squared that we can factor out. And this guy, I got to take out a negative 25. And then I end up with 2m plus 1 times m squared minus 25. When we were doing this stuff before, we would have just left something like this. But now, we can look at this guy right here and say, hey, wait, this is a difference of 2 squared. I know this can factor into m plus 5 times m minus 5. And then this guy can't do anything with, so we're just going to leave him. So this is now the completely factored form of this 4-term polynomial up here. So that was our first weird case of the day. Let's talk about the next one. So in this one, we have perfect square trinomials. These guys have 3 terms, unlike the ones we just got done doing. But these guys are perfect squares because we can write them in something that looks like this. Now when that happens, remember the pattern is your first thing's squared, your last thing's squared, and then in the middle is 2 times a b, so 2 times the 2 different terms that you have. So here's an example of one. 16x squared plus 24x plus 9 is a perfect square trinomial because 16x squared is 4x squared, 3 squared is 9, and then if I do 4x times 3 and double it, I end up with 24. So this says determine whether each trinomial is a perfect square trinomial, write yes or no, and then if it is, factor it. So how we can check this is we can ask ourselves, what would I have to square to get 4y squared? We would have to square 2y. And then what would I have to square to get 9? And we would have to square 3. And then we need to check, does this middle term equal 2 times 2y times 3? So remember, we're getting the 2y from here and the 3 from here, and then we have to double it. So this would give me 2 times 2 is 4, times 3 is 12y, which is what we have here. So yes, this is a perfect square trinomial. Perfect square trinomial. So because of that, these 2 things right here are going to be what we get when we factor it. If I factor it, it's going to be 2y plus 3 all squared. And that's our answer. Now the awesome thing with these is it doesn't really matter if you remember this rule when it comes to factoring, because push come to shove, you could always just factor it the old way. You would end up with this written twice. And then you would say, oh yeah, I know to write that like this. So let's take a look at the next one. So what do you have to square to get 9x squared? That would be 3x. What do you have to square to get 4? That would be 2. And then we need to check to make sure. If we do 2 times 3x times 2, do we end up with 6x? 2 times 3 gives me 6, times 2 gives me 12x. So this is not a perfect square trinomial. So in that case, we can't factor it using this little trick, but we can still factor it if we can find two numbers that add to make -6 and multiply to make 36. And if we run through our numbers here, we need them both to be positive in order to do this. And there aren't any numbers that do this, so this is prime. But just because this doesn't work doesn't mean that there's no way to factor it. Sometimes it just means that it's simply not a perfect square. So I want you guys to try doing both of these on your own. This one's solving, so don't forget how we solve. You got to factor first and then use the zero product property. So your first thing you should do is move this guy, get that over so it equals 0. Make sure you write down any questions you have and we can go over them together in class. Enjoy your night.